Hello, everyone. I'm Sagar Manglani. I'm the perception lead at Telio. Telio is a startup about automating heavy machinery. We modify existing vehicles to make them teleoperate, as well as to provide future capabilities such as autonomy in situations like tramming, auto loading, auto dumping, things like that. So today we are going to be talking about how we can leverage vision language models for automated vision data annotation and specifically in construction environments. So these are the brief topics we'll be covering over. We'll talk briefly about Telio, then automated data annotation, why we want to use VLMs, what are the problems with auto annotations, and what are the possible solutions with regards to that. So as per Jensen's talk at GTC, physical AI is the next major shift that will happen in the world. After agentic AI, that has already happened. Um, and this will unlock a lot of possibilities where you will see AI robots in the real world operating alongside humans. However, whenever we think of physical AI, we tend to think of humanoid robots, and humanoid robots are not exactly the ones that are going to be moving the world around us. When you look at things like this, in environments like construction, where massive amounts of material and load is being moved around, we need automation here. Sorry, I'll let video finish up. So we need automation over here because the industry is facing a massive shortage. Over 90% of the construction firms report that they have difficulty hiring people, as well as more than 40% of the people are going to retire from this industry in the next few years. So Telio is the platform to bring physical AI into the physical world. So we develop autonomy for every type of machine. Doesn't matter if it's a John Deere or a Komatsu. We retrofit these vehicles with Telio kits. We have stations from where one operator can simultaneously manage all of these machines. Here is one short video showing the existing deployment of Telio. This is with Tomahawk Construction in Florida. Even today, right now, they are using autonomy every day to move loads around. This is where one operator is remotely controlling 3 dump trucks. I'm sorry about the lag in the video. So this is one operator controlling these machines. And you can see all of these vehicles are pretty are moving by themselves and they are empty inside. Okay, so now that we have a solution where we have deployed, the advantage that we have is we are able to gather a lot of data through our customers. And to reach the stage of physical AI, we have a massive data gap, but that data needs to be annotated. That needs to be understandable form of data. So this is where automated data annotation comes in. And specifically in today's talk, I'm going to focus on data annotation with vision language models. So what is automated data annotation? Let's say we have a scene over here. This is the same scene that you saw in the video. We have an excavator loading a dump truck. So this is annotation out of a big model VLM called Quen. And this is grounded segmentation based on those outputs. So you can see in the background, there is a car over there. It is detected. You have excavator and dump truck. And we have pixel level identification of what is truck and what is ground and what is excavator. So the general idea over here is you have a data collection pipeline. You collect the data. And from here, we'll assume that you have collected the data so far. Um, The next step would be to do 2D object detection. I'll explain why 2D object detection is still important. We can use that data to later do grounded segmentation. And then later that kind of information can be used to do 3D segmentation based on depth information as well. Now, the reason we stick with 2D object detection is because even though it is considered trivial in the autonomous industry, the thing is that it has become extremely robust, and that is something you really need for data annotation. So one thing we have observed in the real world is that grounded segmentation with bounding box input uh, performs much better than grounded segmentation with just a text prompt. Like if you were to use a model like Florence, you would see that grounded segmentation with a text prompt leads to much more inaccurate segmentation compared to combining something like Quen and SAM. So let's discuss a bit more about the models. So what we need in the model is first, the model should be capable of performing the task that we are looking for. Um, Most of the VLMs understand the images, but they have a hard time creating exact numbers out of it, saying, the object is present at this specific coordinate. So we need to make sure of that. Second is the model needs to have very strong zero-shot performance uh, so that it can operate in an environment like construction, where generally you don't have a lot of annotated data. And third is the model should support fine tuning. Now, the reason this is important is because we want to make sure that our solution is scalable in the end. Just building a model is not enough. That model needs to be able to be fine tuned in a way, say, you observe certain scenarios where the model is not performing well. You should be able to retrain that model so that it can perform in all your environments. So let's look at some of the recent foundational models that we have. The first one is the best model I know so far, which is Quen 2.5 VL, the 32 billion parameter model. This is made by the famous Quen team from Alibaba. Um, Fine-tuning something like this would require about 8 H100 GPUs, each with 80 GB of memory. So it's a pretty heavy lift. Um, the second one is Florence 2 Large. This is made by Microsoft Research, presented in CVPR 2024. Um, this is a relatively smaller model, less than a billion parameters. You can fine tune it with a single H100. YOLO World Large. This is technically not a vision language model. This is a pure vision model. But it is special in a way that it supports open vocabulary object detection. So you can actually ask it anything and it can give you the output that you want. And the best part about it is you can run it on a consumer GPU like 4090. And then we have segment anything too. This is a model by Meta, which lets you take in a bounding box and create segmentation annotations out of it. So these are the four models that we'll be talking about in the coming slides. So let's look at a demo of YOLO World and SAM2. What is possible with that? So you see a truck moving around here. It has the bounding box detected on it, and it has pretty good segmentation output coming out of it. Um, I would say this is pretty usable, but this is also one of the relatively easier scenarios that you would like to annotate. Right. So why VLMs then? Annotating dump trucks is easy because they are very visually similar to trucks. However, if we consider a unique object like this is a trailer with a solar panel. It has a compute inside. It has a raised mast, and there is a radio on top of that mast. Um, this is an extremely uncommon type of object, but it is something that you would commonly see on something like a construction site. So this is where vision language models come in. Now we'll do a demo with this one, and the prompt that we'll give for this one is solar trailer tower. These are like the best terms that I could come up with for detecting something like this. And we'll try out the Florence 2 VLM over here. The source video is relatively smooth. I apologize for the jagged video over here. But if you notice something in the video, there are problems over here. Did you notice something in that video? Sorry. So you would see that there were a bunch of problems in that annotation. Um, Either the entire object is not selected, or the part of the vehicle is selected when it is farther away from the object, or you would have situations where the entire frame is being classified as the prompted object. Now, these are the kind of problems that we want to handle. Uh, so to identify these bad annotations, for videos, we can start tracking bounding box over frames and see when there is a substantial change in the size or the location of the object. But even that is not enough. What if you have a situation like this where a part of the object is outside the bounding box, and this is still not good enough for training because you want your data set to be extremely accurate. As I had said earlier in one of the conversations, your data set is supposed to be holy. Uh, you need to make sure you have a very clean data set. And this is where we again bring in VLMs. Now, where you have a good tracking, you can consider that edge to be safe annotations. But if you start to see some sort of change happening in there where you are not sure whether the object is just moving or it has a bad annotation, you can subject those kind of thresholds to VLM. And if there is a massive change in the annotation, you can simply discard those annotations. Now, it is easy to discard annotations in automated annotation because you are presumed to have lots of data and you don't have the time for human annotation. So for this example, we use OpenAI's GPT-4o to identify which of the objects are within the bounding box and which are outside. You can see some of the examples that the model accepted and some of the examples that model rejected over here. So one thing is we pad the area around the bounding box so that the model only focuses on this specific area instead of the entire frame of the image. Now let's look at how annotations look after the curation. So you can see over here, there are basically near zero instances where there is any problem in the annotation. So let's update the general idea that we had discussed earlier. We build a data collection pipeline, we collect the data, we perform 2D object detection, but now we change where we curate the data before using it for downstream tasks. Then we do grounded segmentation, and then we curate the data again. Then we do other sort of downstream tasks like 3D segmentation, and then we curate the data again. So the learning from here is simply curate your data. And here is the final demo of Qwen 2.5 VL annotations from Qwen 2.5 VL that are passed on to Meta's SAM2 and verified with GPT-4o. So you can see when you have a clean start with a bounding box, you get very clean segmentations coming out of it. So in conclusion, VLMs create new possibilities for annotating object classes that may be never seen before. There are no data sets for it. And those kind of objects generally exist in construction environments. They can also be used to double check your work for mislabeled annotations, as well as these kind of models can power the downstream tasks that can be used for segmentation, 3D object detection, or 3D segmentation. That's all. Okay.
How well does this fine tuning transfer to a different site of the same object? You're training in all the examples were for the same object at the same site. Take that satellite array, put it in a new site. Then still able to detect it with a different background.
Excellent question, by the way. Thank you. So the demo that I showed over here, this is without any fine tuning. And this is completely zero shot. So what you are looking at over here is that this demo is out of a prompt of solar trailer tower, and it has no knowledge of this kind of object. And so I believe it can carry over really well into completely novel environments because of the strong zero-shot performance. So,
Tracking of bounding
yeah.
is
So tracking of the bounding boxes is used to identify whether something bad happened in annotations. And the main objective of using tracking is to reduce your cloud cost, uh, mainly because of that, because you can annotate everything and then send everything to the cloud itself to verify with GPT-4o or Claude models whether an annotation is good or not. But by using tracking, you can start to minimize those costs by only verifying the frames where you saw something substantial change in the scene. Yes, please.
you have like so does the data set like you would except for reject.
Can you clarify your question?
Well, it's a stationary object. You're moving around, so you could use your ego flow estimate and project that in design on.
Yes, that is definitely possible. I was showing just a simple example over here, but this kind of method is applicable in environments where there are dynamic objects moving, there are multiple objects. For simplification of the problem, I showed it with a single object. But in such a scenario, you can use the ego pose estimates, but in dynamic situations, that might not be possible. Yes, please.
Hi, great presentation, by the way. I had one question about the 3D segmentation possibility. I know that you said that you're tending to stick towards the 2D annotation rather than 3D. But given that the results are so good and that it does set the foundation for downstream tasks like 3D mapping and segmentation, are you planning to do any future work creating 3D mapping using this method, or what's holding you back from that?
Right now, this is the amount of information that I can share publicly. We have done work on 3D segmentation and things beyond that. But yeah, that is an extension of this. Yes, please.
I have a question related to the purifying process. For purifying process, do you feed the entire data set to the VLM, or you just feed range or instances that you have potential keep in buckets?
So in general, it depends on how accurate you want your annotations to be. My general preference is to feed only those images where there has been a substantial shift, because there is also another control step that can be used later where once you train your models, you can see that your model does not perform well on certain images. And those images itself can also be reviewed with a large VLM again to verify that those are annotated correctly or not. So there are ways of implementing more checks across the path. And that way, I think you can bring in very good control while keeping the cost minimal for the cloud operations. Yes, please.
Is there any need for human QA, like for the annotations that for these curation steps, or how does the sort of human double checking the work fit into those?
So in this step, the objective that I'm trying to achieve over here is trying to keep human out of this loop as much as possible. And so far, these models, the cloud models especially, are getting much smarter and smarter, and that is helping us avoid that in the first place. So there are some QA checks right now in Telio's pipeline that are verified by humans, but those are only under circumstances where something has gone bad.
Thank you very much.
Yeah, thank you.